Let's talk a little bit here about solenoids. Okay, a solenoid is just a fancy word for a coil of wire. So on the right side here, you can see a loosely wound solenoid. We won't be looking at that. Notice that if we wind the windings loosely, that we get these blue lines are the magnetic field, and that the magnetic field is ununiform in the middle of it, right? But to the extent that we put the windings very close together, okay, we actually will get a fairly uniform magnetic field in the center of this thing. Okay, in fact, it's our very best way of making a uniform magnetic field. Okay, now the direction of these arrows for the magnetic field, right, come from the first right-hand rule we learned, which is that you put your thumb in the direction of the current. So if I put my thumb in this direction, right, my fingers would wrap around, and in fact, when I was here, my fingers would be pointing that way of my right hand, and that's why the magnetic field goes like that. Okay, and what we're going to do is I'm just going to show you how to figure out the magnetic field inside a solenoid based on the current and the number of windings and some of the geometry of the coil here. Okay, so let's go to the next slide here, right, and hit the right arrow. And this is Amperes Law, right? Okay, what that means is that if we pick some path and we add up all of the magnetic field dotted into the length, okay, that's going to equal, if we do a full circle, we got to do the full circle, right? That will equal mu naught times the enclosed current. Okay, now so in this diagram here, what we've done is we've taken a coil and we've sliced it. Okay, we've taken a little slice of that coil, and so this is what current coming out of the paper, and of course this current is looping back over to this guy, right? It's like you, and this guy's looping into this, so it's going into the page there, et cetera, right? We're just not drawing that for clarity. Okay, so what we're going to do is we're going to take this thing and we're going to take the dot product of the magnetic field times the length. Okay, and we're going to say that equals mu naught I. Now understand that the dot product is B dl, right? That is actually equal to B dl cos theta. Okay, so the concept of a dot product is how much of the magnetic field is actually in the direction of dl. Okay, in this case, it's not going to be really dl, it's just going to be L, right? Okay, so let's just do a path. We're going to go this way, right? Okay, for the segment BC, the magnetic field is actually perpendicular to the segment that we do, and so the cosine of 90 degrees is actually 0, right? Okay, because what is it? It's the x coordinate, right? 90 degrees is right on the y-axis. So this for BC we get nothing, right? I'll write it the correct case. BC for line segment BC, it's nothing, right? Because the angle is 90 degrees. And then if we do CD, right, that length is L, and we get that that it's just B times L. That's the integral of BL, right? It's just B times L because it's a uniform field, B, and it's just length L, right? And then for dA, it's 0. And then we'll say, here's what we'll say, is that out here, essentially there's no magnetic field because these lines, these magnetic field lines, sweep way around like this, okay? Or the other way I've seen this done, by the way, is that you extend it. It's a little harder to draw it, but you extend this line out to infinity, right? We go way out here to infinity where there is no magnetic field at all, and there is no contribution here. So BC and DA and AB are 0, and we only have this segment right here. That's the working segment, the part that's in the coil, right? Okay, so for that segment, we've got B times L, right? And then that equals, and then we got to figure this out, right? It's mu naught times I. Well, it's going to be the number of windings, right? It's not just the current in the coil, but we've actually, in this case, encompassed 1, 2, 3, 4, 5 windings, right? In general, it's going to be mu naught times the number of windings, right, that we've encompassed in this case in the distance L, right, times I. Okay. So let me erase that, hit the right arrow, and we'll see the proper formula, right? Okay. So this is the magnetic field inside in the coil, right? Or the solenoid, right? That N is the number of windings, I is the current that's flowing through the coil, L is the length of the solenoid, right? and then L is the length, and mu naught is 4 pi times 10 to the minus 7th Tesla meters per amp. Okay. Now sometimes you'll see that they'll talk about windings per meter, right? And then they use this, which is just kind of a weird formula. I'm just always going to use that one. Okay, but there is you'll see this, right? And so when you look at these big solenoids that are trying to make gigantic magnetic fields, this is kind of an interesting thing because ultimately it depends not on the number of windings and not on the length, but it actually depends on the windings per meter. So if you're trying to make a strong magnetic field, you want a lot of windings per meter. Well, the only way to do that is to make your wire small, right? Because the small wire, you can pack more windings in a meter of coil, right? Or you can make it ridiculously thick, but this is for a thin solenoid, right? So this actually breaks down in that case, right? And then the extent to which you make really thin wires, you can't run a big current through them, right? This is why we tend to, if we really want a good magnetic field, we'll use a superconducting coil, right? But anyway, that's the deal. That's the formula. That's where we got it. And in the next couple videos, I'll just solve a couple problems, okay?